All right, welcome to Next Gen Manufacturing. Today, we're jumping into a topic that, honestly, can make or break a product before it even leaves the drawing board. It's all about a puzzle of precision that happens in these tiny, almost invisible gaps between parts. And believe me, getting this right is absolutely critical.
So picture this. You've just designed the perfect product. I mean, it's beautiful. Every single component is machined to what you think is perfection. But then, the moment of truth, assembly time, and they just don't fit. What on earth went wrong? Well, the culprit is an error so tiny, you literally can't even see it.
Yeah, it turns out those tiny, supposedly acceptable variations in each and every part, they add up, they accumulate, and they can create a massive problem. This whole phenomenon has a name. It's called tolerance stacking. And learning how to master it, well, that's what separates a truly successful product from, a very expensive pile of scrap. Okay, so before we dive into the math and start breaking down the calculations, let's take a step back and really focus on why this matters so much. Because this is not just about getting parts to fit together. No way. This goes right to the heart of the efficiency and, frankly, the profitability of the entire manufacturing process. You can think of it as this incredibly high-stakes balancing act. On one hand, you want super tight tolerances for more precision, but that drives your costs through the roof, it stretches out your manufacturing time, and it creates a ton of waste. So the real goal, the sweet spot, is finding that perfect balance between function, cost, and just, can we even make this thing? You get it wrong, you've got a failed project on your hands. But you get it right, now you've got a serious competitive advantage.
All right, so we get it. The stakes are high. But what exactly is tolerance stacking? Let's really break this thing down.
So in a nutshell, tolerance stacking is really just the method you use to add up all those tiny acceptable variations from a whole bunch of individual parts. See, every single component has this little margin of error. That's its tolerance. And this analysis, it's all about predicting what the total error is going to be when you finally put all those pieces together. A really good way to visualize this, imagine you're stacking Legos. But here's the catch, none of them are perfectly flat. The first one's a little warped, the second one is also just a tiny bit off. You stack a third, a fourth. By the time you've stacked 10 of them, your whole tower is leaning over. That is tolerance stacking. Each one of those small, acceptable errors just builds on the last one, and suddenly you have a total error that is completely unacceptable. So how do we avoid building that leaning tower? Well, there are some really fundamental best practices that can save you from making some super costly mistakes. Let's take a look at the basic rules of the game. Okay, rule number 1, resist the urge to make every single tolerance ridiculously tight. I know it seems like that's the path to perfection, but it just dramatically blows up your costs and complexity. And rule number 2, don't over-dimension a part. What I mean is, slapping a tolerance on every single feature, that can actually create conflicting requirements and make the part literally impossible to manufacture correctly. Okay, now it's time to get into the actual calculations. When it comes to analyzing a stockup, engineers typically use one of two main methods, and each one has its own strengths, depending on the situation. And really, the choice between these two methods boils down to a pretty simple question. Are you a pessimist or are you a realist? See, the worst-case method, well, it's pretty pessimistic. It assumes every single part is at its absolute max or min dimensional limit. Statistical analysis, on the other hand, is much more realistic. It recognizes just how unlikely that scenario is and decides to play the odds instead. So let's kick things off with method 1, worst-case analysis. Now, this method is great because it gives you 100% ironclad guarantee that every single assembly is going to fit. But that certainty definitely comes at a high price. It's really best for simpler assemblies or for those super critical applications where failure is just, it's not an option. Okay, let's walk through a quick example so you can see how this works. To find the absolute minimum width of, say, a slot, we have to assume every single feature is at its smallest possible dimension. So we'll start with the left radius. It has a tolerance of plus or minus 1/1000th of an inch, so its minimum size is 0.124 inches. Okay, next up is the middle flat section. That has a tolerance of plus or minus 0.02, so at its absolute minimum, that's 0.248 inches. And finally, we have the right radius, which has the exact same minimum dimension as the left one, 0.124 inches. Remember, what we're doing here is planning for the absolute smallest this assembly could possibly be.
All right, now for the easy part. We just add all those minimums together. And what we get is a total lower limit for the slot of 0.496 inches. And the key here is we know with absolute certainty it will never be smaller than this. Now you do the exact same thing for the upper limit. You just add the maximum tolerance for each part. When you do that, you get a total upper limit of 0.504 inches. So we know the slot will never, ever be wider than that. So, by combining that upper and lower limit, we finally get our worst-case tolerance. The target dimension, or nominal, is 1/2 inch, with a total tolerance of plus or minus 4 thousandths. And there you have it, a 100% guarantee that every single part will fall somewhere in that range. But like we said, that 100% certainty gets really expensive, especially when you're dealing with complex assemblies that have dozens, maybe hundreds of parts. And that is exactly where statistical analysis comes into play. This method uses probability to find a much more realistic and, crucially, more cost-effective tolerance. Yeah, this is such a great way to think about it. The whole idea behind statistical analysis is that the odds of all the parts being at their maximum or minimum tolerance at the exact same time, well, they're astronomically low. It's all based on the good old bell curve of normal distribution. But to get there, you first have to normalize all the different tolerances. It's kind of like grinding different sized coffee beans to get a uniform consistency before you can brew them. So by using a formula, it's often called root sum squared, which combines all the variances. You don't get a single guarantee anymore. Instead, what you get is a set of probabilities, or confidence levels. For instance, you could design for a 99% confidence level. That means you're accepting that, okay, maybe 1% of assemblies might fail, but the other 99% will fit within a much more achievable tolerance, something like plus or minus 2.4 thousandths. This is huge because it empowers engineers to actually balance the risk of failure against the super high cost of that 100% guarantee. Okay, so we've covered the why, the what, and the how. Now let's pull this all together and think about what this really means for the future of manufacturing. At the end of the day, this isn't just some math problem for engineers to solve. It's a genuine strategic skill. It's about navigating that tricky, crucial space between what you designed on a computer and what can actually be built in reality. Mastering tolerance stacking means you're making smart, data-driven decisions that impact everything from the company's bottom line all the way to your customer's satisfaction. And as we keep moving toward this future of automation and totally data-driven production, understanding these fundamental principles is more critical than it's ever been. Sure, machines can execute commands with incredible precision, but it's still the human mind, it's us, that has to define the parameters for success. How we choose to manage these tiny, invisible variations, that's what will ultimately determine the quality and the success of everything we build.